In this problem, we are launching perhaps a cannonball out in the desert, maybe, where we have a cliff and then a shelf and then another cliff. And the question is, how long will this projectile remain in the air? This 84 meters per second is v sub x, the velocity in the x direction. Because we are launching it horizontally, you can see the vector here that's drawn, that is a horizontal vector. Then we know that Vy initial is equal to 0 meters per second. What that says is the projectile isn't being launched upward or downward initially, only in the x direction. We're going to assume that we're on Earth here, so that would mean that the acceleration in the y direction has a magnitude of 9.81 meters per second squared. Again, leave a little space here in front of the 9.81 because we have to choose a sign convention that is going to work. However, we don't know right off the bat if this cannonball is going to clear the shelf. It might land on the shelf or it might clear it. And obviously that's going to affect the amount of time that the cannonball is in the air. dy, therefore, the displacement in the y direction, is either going to be 105 meters, that is, if it lands on the shelf, or it's going to be 210 meters if it clears the shelf. I think what we should do then is refer to our equations. By the way, the day that I came up with this, that was my best day. We're looking for time. We know the displacement in the y direction. We're going to have to do two calculations. We're going to do one for a dy of 105 meters, and then we're going to have to do another one with a dy of 210. We know the acceleration in the y direction, 9.81 meters per second squared, and we know the initial velocity in the y direction to be 0. We also know that the cannonball was launched at 84 meters per second horizontally. Right there. How would we find time? We can't use the leftmost bubble to find time because we don't know dx. So let's use the rightmost bubble. What equation will apply? I think it's the one on the bottom. dy, vy initial, ay, and we're looking for time. Let's use that one, and we're going to do it twice. Once in case the cannonball lands on the shelf, and once in case it clears the shelf. Here we go. dy is equal to vy initial times time plus 1/2 ay time squared. Now here's the thing. All of the up and down motion is pointing downward. Gravity points downward. The dy points downward. And so for this, I'm going to say that downward is positive. We're free to do that, which means this acceleration is going to be 9.81 meters per second squared. We're going to have one dy that's equal to 105. And then we're going to have a second dy that's going to be 210. That is, if it clears the shelf and it lands on this part that's on the far right side of the screen. Vy initial is 0, which means that time is equal to 2 dy over ay square rooted. Let's do that with a dy of 105. 105 is positive, 9.81 is positive. You can see that if we had chosen upward to be positive, then this 105 would be negative, and this 9.81 would be negative, and that would work out just as well. To two significant figures, this comes out to be about 4.6 seconds. That is the time that that the cannonball will be in the air if it lands on this shelf. If it clears the shelf, however, then that time is going to be 2 times 210, because it will go downward 210 meters, right here where I'm pointing in the upper part of the screen. 105 plus 105, that's 210. Make sure you take the square root of this entire product quotient thing, not just the square root of 2 or the square root of the numerator. That comes out to be 6.5 seconds. Now the question is, which one is it? Well, we don't know yet. But why don't we take into account this 330? That is a dx, isn't it? Essentially, that is a dx. So what we can do is we can now take these times, in particular this one, and let's see how far in the x direction this cannonball has gone in 4.6 seconds. Let me write that right here. Dx in 4.6 seconds equals question mark. How far has it traveled in 4.6 seconds? If that number is less than 330, then clunk, the cannonball is going to land on the shelf. If this number is greater than 330, then it will have cleared the shelf. So let's figure out how far in the x direction this cannonball goes in 4.6 seconds. And to do that, look at that. We go back to our Venn diagram here. Now we know the time, 4.6 seconds, and we can very easily calculate dx. So let's do that. Dx equals Vx times time. Vx is 84 meters per second, and in 4.6 seconds, the second units cancel. That comes out to be 390 meters, which means in 4.6 seconds, it's well beyond the edge of the shelf. At 4.6 seconds, if 330 meters is right here, then 390 meters is about right there. That's where the cannonball is at 4.6 seconds, which means it definitely clears the shelf and therefore will be in the air for this amount of time, 6.5 seconds.